Welcome to the lectures on fundamentals of MIMO wireless communications. We are discussing spatial diversity. In the previous lectures, we have talked about receive diversity as well as transmit diversity. For the transmit diversity case, we have discussed the condition when channel is known at the transmitter. Now, when the channel has to be known at the transmitter, we should remember that there is this transmitter with several antennas and there is, so let's say the simple case when there is one receive antenna. This is the most simple case. So at this case there was a W1, a W2 up to WMT that was used at the transmitter. That means we had weight factors and these weight factors were proportional to the channel gains. So if this particular link was H1 and the last one was HMT, so we had all these links. So this entire channel vector H had to be fed back to the transmitter. Now this is significant, that so for this to happen, one must understand that the channel has to be estimated at the receiver. So channel estimation, if we typically take y is equal to hi times s plus n, we need to estimate all of these channels. One way of doing it could be that we send a signal from here, let's say s is equal to 1 from this. In that case, we would get an estimate of h1, and then we would set s equals to 1 from channel 2, from antenna 2, and so on up to all the antennas, and then we will be getting h1 cap as the estimate, h2 cap as the estimate, up to hmt cap as the estimate. So all these channel coefficients have to be estimated in step number 1. In step number 2, these channel estimates have to be fed back to the transmitter. And the implicit assumption that we make is that these channels that are estimated, then they are fed back and which are used in MT during subsequent transmission. So that means it's first period when you channel estimate the channel estimate for all links is pretty good amount of time. Then there is feedback followed by the subsequent section when you do transmit MRC. So this is the total interval of time, and in the previous case we have assumed that there is perfect channel estimate. That means channel is completely known at the transmitter. So when channel is completely known at the transmitter, one has to be very careful regarding what is known about the channel. So if this duration of time, let's say this duration is t, if let's take the case 1 when t is greater than coherence time, what's going to happen? In that case, channel that is estimated in this part, that means h of T1, here let's say this is H1 of T2, and here it is H1 of T3. These are three different times. If T3 minus T1 is greater than coherence time, this coefficient is very different from the coefficient that was measured, whereas this is used in W1, the weight. So if this is used in W1, in the expression that we have written, we said that H1 at time T3, we did not use the time T3 in that expression, times H1 at times T1. We made the assumption that these two are equal, and we said it is equal to mod H1 squared. But that's not going to happen. So one of the fundamental conditions that should be valid for it to work properly is that this total time must be less than the coherence time. That's number 1. Number 2 is that this is a valid condition for it to work. This feedback has to happen in an ideal way. That means during feedback there is no error, and so no feedback error. And point number 4, that the channel estimates are perfect, although it is never true. So what we discussed is an ideal condition. That means when you are estimating the channel, let's take this example. So say S is equal to 1. So what do we get is Y is equal to H1. That means I'm transmitting through only antenna 1 and not transmitting anything through these antennas, H plus N, right. So basically this Y, I am saying that H1 cap is equal to Y. So this is equal to H1 plus noise. That means there is some noise in it. In a very trivial sense, if I have sufficient large number of such recordings, I can reduce the impact of noise, but I cannot eliminate it. So under true conditions, true operating conditions, this estimate is never perfect. There will be some noise. So we have made this perfect estimate, and that is the result that we have given. So when we do transmit MRC, we have a lot of difficulties to overcome. That means we need this coherence time to be pretty large. We need ideal feedback, that means almost instantaneous feedback without any errors, and we require perfect channel estimates. But in reality, this is not easy to achieve, because even during feedback you would require channel estimates and so on and so forth, everything to be going on. So this is not a very much desired operating condition. We would love to use it, but because of constraints it is very difficult to use. So under nearly static conditions this is fine, but under dynamic conditions there is a lot of difficulty in this. So to overcome this, there are mechanisms by which you can obtain diversity gain at the transmitter without channel knowledge. At Tx. Now this is very, very important. So we are not assuming any channel knowledge. So that means we are avoiding this whole process of feeding back channel information, using which one would be sending the communication signals. So we are assuming it's not there. So something better has to be done at the transmitter where H is not used. So that is the domain that we are going to look at. So we will take a look at a very, very simple situation, and we'll assume that let there be 2 antennas at the transmitter. This is the minimum number of antennas that you can have in order to obtain spatial diversity, and let the receiver have only 1 antenna. So this scheme is a very, very special scheme, and this was proposed by Alamuthi, and this scheme is known as the Alamuthi scheme. That is what we are going to discuss in this particular section. So under this particular case, what is done is we will consider 2 time instants, T1 and T2, and we'll say this is the antenna 1 and this is the antenna 2. So in the first symbol duration, we will be sending the signal S1 and S2 from these 2 antennas. So we have two signals, S1 and S2 to be sent. So in the first time instant we are going to send the signal S1 from the first antenna. In the second time in the second antenna we are going to send the symbol S2. In the second time instant we could send the signal minus S2 conjugate, and we can also send S1 conjugate in the second time instant. So when we receive the signal at the receiver, so what we are going to see is that Y1 that is received in the first instant is root over ES by 2, because we have 2 antennas, we are dividing the power equally amongst them, through H1 times S1 plus root over ES by 2 H2 times S2 plus N1. Okay, this is the noise in this time instant 1, and Y2 is equal to root over ES by 2 H1 times S2 conjugate with a minus sign. That's what we are going to send, plus root over ES by 2 H of 2 to S1 conjugate plus N2. So this is what is going to happen, or rather we could say that this is time instant 1, this is time instant 2. So this link is basically H1, this link is basically H2. So he devised this particular mechanism where we are sending 2 symbols in 2 instants of time, and encoded in such a way that in 2 time durations we are sending a total of 2 symbols, that is S1 and S2, because these symbols are modifications of S1 and S2. This is S1 conjugate, this is minus S2 conjugate. So basically overall we are sending 2 symbols S1 and S2 in 2 time instants. So that means we are not reducing the rate, we are keeping the rate constant. So if we see this signal, we can form a vector y in terms of these signals. So to do it better, we would rather use y2 conjugate. So when we use y2 conjugate, we would get root over es by 2, and I would bring this expression here first. So I would have h2 conjugate s1 and a minus root over es by 2 h1 conjugate s2 plus n2. So if I would focus on y1 and y2 conjugate and the received signal, received vector y, I could form it as y1 y2 conjugate, which I could write it as root over es by 2, and I could send signal s1 and s2 from these 2 antennas. I could effectively write the expression in this way, that root over es h1 s1 plus h2 s2, and then y2 conjugate is equal to h2 conjugate times s1 minus h1 conjugate times s2 plus n1 n2 conjugate. So when I write the expression in this way, we effectively are writing y is equal to root over es by 2 h effective, this is the effective channel, times s, this is a matrix, plus some noise vector. So we have a linear equation, so we could use matrix algebra in working on this. Now to get a solution, one of the easiest ways would be to have our equalizer, where the equalizer is h effective Hermitian multiplied by the received signal. So if we multiply this with the received signal, what we would get is root over es by 2 h effective times hef times s plus heff, that is the h effective Hermitian times noise. So we are multiplying this particular coefficient. So if you expand this coefficient, what you would get is, let us first write down this h1 h2 h2 conjugate h1 conjugate with a minus sign. The Hermitian of this would be h1 h2, this row becomes this column, this row becomes the next column. So there is a conjugate transpose, so h1 conjugate h2 conjugate, h2 will become h2 and a minus h1, right, times s and so on. So we'll focus on this particular product. What we see is that we are getting h1 mod squared plus h2 mod squared. The second term would be h1 conjugate times h2 minus h2 times h1 conjugate. So they cancel out each other, we get a 0 there. So when we take at this row times this column, h2 conjugate h1 minus h1 h2 conjugate, so again we get a 0, and we have h2 mod squared plus h1 mod squared. So what we get effectively is h1 mod squared plus h2 mod squared times 1 0 0 1, which is an identity matrix of size 2. So this is basically h f squared times I. So we can say that h effective that got created here, this is a orthogonal matrix that could have been seen before also, and that's what we are seeing here as well. So in this way, if we proceed, we could write this expression here as root over es upon 2 times hf squared times I times s plus h effective eta bar. So this is the vector y that is received. So if we look at this expression, so this is S1 S2 1 0 0 1 HF squared times square root of ES by 2. So we have this signal S1 coming out into Y1, and which is not interfered with that of S2, and of course there is this processed noise, so we could write it as n tilde bar. And now we'd like to calculate the signal to noise ratio for this particular case. So we need to also calculate E of n tilde Hermitian, and this would turn out to be, from this we can clearly see it would turn out to be HF squared n naught times I2. So that means here also we have this particular coefficient, n naught is the variance and I2, that means it is identity matrix. So each of the noise coefficients are HF squared times n naught. So if you have to calculate the signal to noise ratio for each of the branch, we will be getting ES by 2, this squared divided by this squared, so it's basically HF squared times, and this n naught will turn out in the denominator. So we have ES by n naught half HF squared. So this is the effective SNR because of Alamuthi scheme that we get, and which will be useful for us in calculating the error probability expression. So if we move ahead further and we look at the probability of error expression, so PE we said it is approximately equal to NE bar times Q function of square root of gamma combined d mean squared by 2, or you could also do it in terms of alpha m and beta m. So this is less than or equal to NE bar e to the power of minus d mean squared by 2 times the combined, and we would be interested in PE bar. So PE bar you would approximate it to be NE bar, and this one is clear, it is product of I equals 1 to MT. MT is equal to 2 in this case, 1 by 1 plus this particular expression is sorry, we need to expand this NE bar e to the power of minus d mean squared by 2 and gamma bar times sum of h I squared I equals 1 to 2. So we have 1 to 2 gamma bar d mean squared by 2, right? So that is equal to NE bar. We have a 4 over here, 2 times we have a 4 over here, 1 plus gamma bar d mean squared by 4 raised to the power of 2. And if you look at the average expression from this, Alamuthi average is equal to half ES by n naught times this, that means expected value of HF squared. This is basically H1 squared E of H1 squared E of H2 squared mod, of course. So this is equal to 2. So what we have is ES by n naught. So what we see in this case, there is no average increase in SNR compared to the previous case where there was an MT at the transmitter. So with this we have, sorry, just a second, we have y bar half of this, half ES by n naught. So we have missed out a 2 over here, so this would be gamma bar by 2, because this particular expression is gamma bar by 2 HF squared. This 2 we had missed out, this 2 comes over here, this ES by n naught comes over here. So when we take this expression, this is fine. When we move for gamma, NE bar is NE bar e to the power of d mean squared comes over here, 4 comes over here, this expands to gamma bar by 2, sum I equals 1 to 2 mod hi squared. So we have an 8 in the denominator. So 2 times 4 is 8. So we have a 8 in the denominator, and we have 8 in the denominator. So this approximately, when gamma bar is much greater than 1, you have any bar gamma bar d mean squared upon 8 to the power of minus 2. So if you would have had a transmit MRC or a receive MRC, you would have had any bar gamma bar d mean squared by 4 raised to the power of minus 2. So clearly you can see there is a factor of 2 that is different over here, and that would be evident if we look at the error probability curves for these things. So what we clearly see here is that the average SNR that is experienced in these two cases, this is for MRC, where it is transmit MRC or receive MRC, and this is for Alamuti scheme, where there is no channel state information at the transmitter. So there is a change in the average SNR. So in MRC you can clearly see there is an increase in average SNR compared to transmit MRC, whereas the order of diversity is the same in both of them because they have these 2 branch antennas. So we are combining MRC when number of branch antennas is equal to 2 with this case. So if we would look at the error probability expression or the error probability curves in this case, we'll get some performance like this. If this is the SNR in dB and this is the probability of error expression, so when there is no diversity, suppose this is the error probability curve, if we have the Alamuti scheme, we are going to get curve which is going like this. It is giving increase in slope because you can clearly see over here there is this exponent, whereas when we are getting the MRC, what we are having is along with the increase in slope there is an average increase in SNR. So the array gain is also there. So this is the case for MRC, this is the case for Alamuti scheme 2×1, and this is no diversity. So this is the kind of gain that you would observe between Alamuti transmit MRC and receive MRC. So sorry, between Alamuti scheme and MRC be transmit MRC or receive MRC when number of branches is equal to 2. Now since the slope is the same between this and this, the order of diversity is the same, but here there is an additional gain which is an array gain that is present because of the coherent combining that is available in case of MRC scheme. So what we have seen till now are in spatial diversity modes, you could have channel state information at the transmitter, as well as without channel state information at the transmitter you could also gain diversity. But with the special scheme that we have considered, Alamuti scheme, which is a very simple scheme, you can get the same order of diversity gain, but the array gain is not available, which is there in case of channel state information being available at the transmitter or in case of receive MRC. Just I would like to add at this point, when we are considering the transmit MRC case, that means we are considering this expression, this particular scenario, or we can look at this particular scenario. This is very useful. Just if we like to imagine the situation where there is a base station and it is enabled with multiple antennas, whereas the user device is enabled with a single antenna, and we'd like to do that because we'd like to have more processing capability at the transmitter, more cost at the transmitter. At the user end, we would like to have lower cost. So we could use 2 antennas, and we could use 2×1 transmit MRC or 2×1 Alamuti scheme, by which we could gain order of diversity. And because we are having this order of diversity gain, definitely when compared to a CISO scheme, one would be able to get a better PER performance over a single input single output transmission mechanism. So with this, what we have is, even without knowing the channel at the transmitter, you can improve error probability at the receiver by using a special coding scheme where we send 2 symbols over 2 symbol durations across 2 antennas. So again, we'd like to take a look at what we are doing. So what we are doing is here, if you see overall there is S1 and S2 in these two symbol durations, not more symbols. So basically we have two symbols in two time durations, two time intervals. So that means we have one symbol per time interval. So basically we are not losing out in terms of our symbol rate. At every time we are using the channel, we are sending one symbol, as in the case of CISO, and we are getting the full order of diversity. Means in this case there are two diversity branches, we are able to get second order of diversity, because in the error expression we can clearly see that there is this 2 in the exponent. So what we have achieved is the full rate, that means the maximum rate that is possible, one symbol per symbol duration, as well as we have achieved 2 order of diversity, that means the maximum order of diversity. So with this particular special scheme, you can achieve a full order of diversity as well as full rate, and no other scheme can give you this kind of diversity order and this kind of rates. There are many other coding schemes when the number of transmit antennas is more than 2. It may not be possible to see it in this particular course, but you are now ready through what we have discussed to understand those typical coding schemes by which you can achieve diversity at the transmitter by using more than 2 antennas, and you could achieve a little bit of array gain if it is possible, or in most cases array gain is not achievable. If you add more antennas at the receiver along with this, you can potentially get array gain along with diversity gain using transmit and receive antennas both. Thank you.